guess what? I wasn't actually recording any of that. The computer was just sitting there doing nothing. I could have sworn I started that. So here's what I'm going to do, since there's still a few people. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, there are 2 people missing. So I'm just going to... Okay, so whoever is watching this, there, pause it and read that screen. Or read this board. And now... Again, this is one class. Everything goes wrong. All right. So, derivative with respect to x of f composed with g is, and I'll write this in words first. Derivative of f evaluated at g is how you remember the chain rule from calculus 1. Derivative of the outer evaluated at the inner function times derivative of your inner function. Okay. Now, in this case, f, capital F, is a function that has multiple inputs, 2 inputs, only 1 output. So the derivative would be the gradient of f. And I've mentioned a gradient vector before. It's a vector of all partial derivatives, and I'm going to write that down in a moment. The gradient is going to be one of the most important concepts in this entire course. So it's something you definitely have to get used to. And then a derivative of the that's g, derivative of the inner function, we just differentiate both components with respect to x. Well, the first component is only x, so we're just going to get a 1 there. And then derivative of y with respect to x is just dy dx, because we don't know what y is. Okay. Now, the gradient of f, and again, it's something very important for you to remember because it's going to come up all the time, is it's a vector of all the first partial derivatives. And I'll write that down for you. We have just 2 of them in this case. Partial of f with respect to x, partial of f with respect to y. And what we end up doing in this case is when we are multiplying together, it's good that I write a dot here because what is actually happening is another very important thing for you all to know. Dot product of vectors. You learned about this in Calculus 3, and in fact, it's going to be used a whole lot more in this class than it was in that one. So dot product is something you definitely have to be accustomed to. Also, in Calculus 3, you learned about the cross product. Hopefully that at least rings a bell, even if you don't remember it. We're going to be using that a lot later on, too. But the dot product is really the most important. And how does a dot product work? For any 2 vectors, you multiply corresponding components, however many of them you have. In this example, I'm writing here 3 of them. And then you add them all up. And that's what I was doing on Monday for dot product. When I was saying, go across the row and down a column, I'm multiplying this with this, this with this. I move from left to right here, up to down here. Multiply them, add them up. So it's this vector, dot product with this vector, it's just written differently. Generally, we think of vectors as being written as column vectors. So we have partial of f with respect to x times 1 plus partial of f with respect to y dy dx. So that's what we get from the chain rule applied to this equation. So if we go back to the original equation, big F of x, y of x equals 0. I take a derivative of both sides with respect to x, and this is what I get. Partial of f with respect to x plus partial of f with respect to y dy dx. Okay. and then differentiating the right side 0 gives us just 0. So now we can solve for dy dx, because that's what we really want here. Dy dx is minus partial of f with respect to x. What?
Oh, sorry, I was just...
Okay. The other thing I want to point out here, and this is a deliberate choice on my part notation-wise, I've written the partial derivatives one way here, and a different way here, because both kinds of notation, I still sense that some of you are not as accustomed to this as you need to be. It's very important that you are, because again, we're using this all semester long, so your mind has to be able to switch back and forth between whatever notation happens to be used in whatever problem and so forth. Okay, so we have a formula now for the slope of a tangent line, as long as, of course, the denominator, partial of f with respect to y, is non-zero. So if we now apply this to the function that we have, x squared plus y squared minus 4, so now we can go ahead and fill that in. So dy dx is equal to minus fx over fy. What is the partial of this with respect to x?
That, just 2x.
Yeah, it's 2x. And partial with respect to y?
2y.
2y. So he gets minus x over y. So at any particular point xy on the circle of radius 2, the 2's cancel out. The slope of a tangent line is minus x over y, provided that y is non-zero. Okay. Now, okay. What happens when y is 0?
Undefined.
What?
It's undefined.
It is undefined, but from a point of view of the tangent line, I'm going to reproduce the picture. Here's our circle. Okay. So if you look at the points on the circle where y happens to be 0, this is radius 2. So at those particular points that I've marked there, our dy dx is undefined. But what would the tangent? There's still going to be a tangent line. What would a tangent line look like in those two cases? Because if I draw a tangent line somewhere else, like this, yeah, something like that. But at those points, what would a tangent line be?
Just a straight line.
Up
and down.
All lines are straight.
I mean,
All students do that. I can't resist. Sorry, you were saying?
A vertical line?
Yes.
Undefined slope?
Yes, and that's straight up and down, as like you said. Yeah, it's vertical in these two cases. All right. So, so in fact, what you can say is, when you do this implicit differentiation to get slope, get dy dx, if the denominator is 0, but the numerator is non-zero, that's a vertical tangent line. If it's the opposite, the numerator is 0 and the denominator is non-zero, what would happen in that case? What kind of tangent line is that? Yeah, it's horizontal. Yeah, so like an x equals 0 in this case. Here, horizontal tangent line. Horizontal. Okay. Any questions about getting dy dx? So you have a function of two variables, f of xy equals 0. So you have an implicitly defined function like this. This is your formula for the slope of a tangent line. All right. Now, one other thing worth pointing out is if this is my point on the circle, xy, If I draw this line right here, can anyone tell me what this line right here, can anyone tell me, in terms of x and y, what is the slope of that line? It is y over x, rise over run. Now, if you have a slope of this is something you would have learned like a long time ago. If you have a line of slope m, so any line like this, and slope is m, and I want the line that is perpendicular to it. If this line has slope m, what's the slope of that line?
Negative m.
Negative what?
M. 1 over m.
1 over m. Yeah. Minus 1 over m. And sure enough, that's what we have here. This slope, this line has slope y over x. The tangent line is perpendicular to it. And it's minus the reciprocal, minus x over y. Okay. Now, so this is how you handle a tangent line. And you could do a similar thing if you have more variables, more independent variables. Like for instance, suppose you are in three-dimensional space. And you have z defined implicitly as a function of x and y. Instead of just y as a function of x, what is the equation of the tangent plane? And it's very similar. Now you have capital F of x, y, z is equal to 0. So these x and y are now independent, and z is your dependent variable, and you carry out the same chain rule. So you have partial of f with respect to x, and then you don't bother with y because you're differentiating with respect to x. Y and x are independent of each other now. So you move on to z, partial of f with respect to z, and then partial of z with respect to x. Before I did dy dx, because y depends on only one variable, x, that dy dx tells you everything. Z depends on two variables. That's why I'm using a partial symbol here. Equals 0. And then also with respect to y, same idea. Partial with respect to y plus partial with respect to z, partial of z with respect to y, also equals 0. And then you can just go ahead and solve these for partial of z with respect to both x and y. So zx equals minus fx over fz. Zy is minus fy over fz. And here it's required that partial of f with respect to z is non-zero. And this allows you to describe a tangent plane. So as an example, I have the implicitly described function x squared z plus z squared y minus 2xyz plus 1 is equal to 0. And just to make clear, that's a 2. So I want to be able to describe the tangent plane to this surface, because this is a implicitly described surface. So it's like z equals function of x and y. We just don't have an explicit formula for that function. So we could go ahead and use these formulas. So partial of z with respect to x is minus fx over fz. So what is the partial derivative of this with respect to x? 2x z to yz. Yeah, because you're differentiating with respect to x, everything else, including yz, is treated as a constant. And that's it for the numerator. What's the denominator?
Just x squared plus 2cy minus 2x.
Not
2xy.
Yeah, 2xy, yeah. Okay, and that's your formula for partial z with respect to x. If you have any point on the surface, x, y, z, you can plug in all three coordinates into here and get that part of the equation of the tangent plane, and then partial z with respect to y will be worked out in a similar way. Okay. So I pick a specific point. So this is a point that is on this surface. X, Y, Z is equal to 1, 0, minus 1. Okay. So what you can do is plug all of these coordinates into here. Okay, so it helps that y is 0. So what would you get?
-2 over just 1.
Yeah, so we get the, and then I forgot, yeah, oh, sorry, there needs to be a minus, my bad, forgot that earlier. So, yeah, minus all of this, yes. Okay, so partial of z with respect to x turns out to be positive 2. Now, the formula for partial of z with respect to y, okay, so don't forget the big old minus out front, would be fy over fz. Now, fz is the same. I'm just going to rewrite that down here. And then partial of this with respect to y is going to be z squared minus 2xz. So now you can plug in x is 1, y is 0, z equals minus 1. And what are you going to get in that case? Well, you know what your denominator is from before. That part doesn't change. There's just a numerator. No?
-3.
Yeah, all told -3. So you have minus 1 squared, which is 1, minus 2 times minus 1. So you get, this fraction turns out to be a 3, but then there's a minus here. And you get a minus 3. First, any questions about how we got these numbers before I do anything with them? Now, what do we actually do with them? You can now write the equation of a tangent plane. So, at this point, now the general equation is z minus z naught equals partial of z with respect to x times a change in x, x minus x naught, plus partial of z with respect to y, y minus y naught. So now we can fill in everything. So for x naught, y naught, z naught, that's this point right here. And then we have our partials of z with respect to x and y. So we'll have z plus 1 is equal to dz dx, which is 2, x minus 1, plus minus 3, y minus 0. So that is, so this problem is, you'll find the tangent plane. This is the final answer. So it's very similar to how you build the equation of a tangent line. You get your dy dx, and you have your point slope form. Y minus y naught is equal to slope times x minus x naught. So this just takes that one step further. you have a term for x and a term for y. Otherwise, it's no different. Okay. Any questions about tangent lines or tangent planes? Is there one more problems about that? Okay, now, what legitimizes all of this is the implicit function theorem. So I just want to state what that is. Okay. Version that I have. Okay. All right. So I'm going to state it in different forms. One that's more specific than the general case. So for this kind of equation, f of x, y equals 0. So the implicit function theorem that states that if the partial of this function, big F, with respect to y at a given point, x naught, y naught, is non-zero, and if the partials of both partials of f with respect to x and y are continuous, which for functions we deal with in this kind of class they generally are. So if they're continuous, forgot a word, near that point, then we can say that this equation, f of x, y equals 0, implicitly describes y as a function of x, at least near this point. Now, that doesn't mean you can come up with a formula for y as a function of x. Depending on the example, maybe you could, but the point is, there is that proper relationship, y as a proper function of x. Okay. And also we can say that dy dx is going to be defined, and we know what it's equal to, so minus fx over fy. Again, at least near this point. Once we wander too far away from this point, you have no assurance. Okay. Now, for the other case, we're dealing with tangent planes. It's a similar. The theorem would have a similar statement. We require that partial f with respect to z be non-zero at a certain point on the surface, and then you can define partial of z with respect to x and y under similar assumptions. Now, we've seen already that if this condition fails, partial f with respect to y is equal to 0, that's where we get things like vertical tangent lines. So it only makes sense that when we have this equal to 0, we cannot describe y as a function of x, because for y to be a function of x, the curve has to pass what test? Vertical line test. So if you have a vertical tangent, it's not going to. All right, so that's why this condition is particularly important. Now if this happens, you may not be able to describe y as a function of x, but what might you be able to do instead? So, because maybe you have a vertical tangent line, there's no dy dx, but you could go the other way. Maybe you can describe x as a function of y near that point, as long as partial derivative with respect to x is non-zero. So for curves that have funky behavior like this, curve like this definitely does not pass the horizontal or vertical line test. Maybe you could go back and forth. Like maybe this piece right here, you could say y is a function of x. Whereas for this piece right here, you can say x is a function of y. So maybe you can decompose a curve into different pieces where you always have the option of doing one or the other. And then you can still define a tangent line, because regardless of what kind of a function it is, there's no denying that for this example, at any point along this curve, there is a well-defined, if badly drawn, tangent line. Later when we get to the next section, directional derivatives, I can tell you how you define tangent lines and tangent planes without worrying about whether you could define y as a function of x or vice versa. So there is an easier way. We're getting to that, but we're not ready for that yet. Okay. All right. Now, every case that I've talked about here, you only have one dependent variable. So it was y in this case, and then for the case of a surface, the dependent variable was z. The implicit function theorem also you can also define it, state it in a case where you have more than one dependent variable. So suppose we have an equation like this, with 4 variables altogether, f of x, y, z, and w, equal to 0. And these are your independent variables, x and y, and you have 2 independent variables, z and w. So is there a way to tell whether you can define z and w as a function of x and y? And you might think, okay, so when do we have zw, I'm writing this as a vector because we have 2 variables here, as some function of x and y? And you might think the condition is maybe you need partial of f with respect to z and partial of f with respect to w being non-zero, because that would be similar to what we've required before. But it turns out that is actually not the condition. Instead, in order for this to be possible, and I want to preface this by saying I'm only talking about this for a couple minutes, FYI. This does not come up in the homework. So I just want to, for completeness sake, if I were to write down the partial derivatives of, okay, so before we have partial with respect to z, or does that have to be a vector valued function? Okay. Yeah, this is it only makes sense as a vector value function. Instead of having just one equation like this, we actually have 2, because we have 2 dependent variables. So this would be like f1 and f2 of x, y, z, and w, and x, y, z, and w. Okay. So if you look at the partial derivatives of both of these functions with respect to both z and w, so f1 up top and f2 down below, with respect to z in the first column, with respect to w in the second column. This is a 2 by 2 matrix. It has to be an invertible matrix. So here we need this to be, basically, you have to have something that you can divide by. We can only divide by something, a number that's non-zero. We can only multiply by the inverse of a matrix that's invertible. And this is in my notes. It's discussed in detail there. Because it's not in the homework, I'm not going to really spend time on it. There's no need. And I don't want blood to start coming out of your ears. But again, just to complete the picture, that this, we have an implicit function theorem for any number of expressing certain number of dependent variables in terms of however many number of independent variables you might have. Okay. All right. Now, during the remaining time, so I guess on Friday we'll get into directional derivatives, being able to take a derivative with respect to any direction, and then we'll see an easier way to compute tangent lines and tangent plane equations. Are there any because right now we have the homework on tangent lines, tangent planes, linear approximations. That we didn't do today, right? Okay, yeah, just making sure. And then the next assignment on this section is due on the 19th, but because I didn't finish this section until today, I'm open to pushing it back if need be. So I'll be checking on how you guys are doing on that. Does anyone have any homework questions on either one of those sets?
It's very tedious on one of them.
Yeah. And I was telling some of you before the rest of you came in here, the homeworks are going to get shorter in terms of number of problems. So just to make sure that the average amount of time spent doesn't get excessive for a 3 credit hour course. Yeah, because there are like 20 problems or something like that. Yeah, so get down more towards the order of like, maybe 10 or 12. So those problems can still be long because multivariable, like I said, by nature is tedious. You did integrals in Cal 2. In this class, you'll be doing double or triple integrals. Similar manipulations just takes more time. But if you guys are simply not, are just wanting to get out of here early, if you have homework questions, you're welcome to ask them.
I wrote it down about part C of number 9, but I can't remember what it was. I wrote down to ask you, but I don't remember what it was.
Dang, okay. Well, if you remember it later.
I can look it up on my computer.
While she's pulling it up, anything else? Other questions? Of course, I told to get out here early. Okay, I'll dismiss class, but anyone has a question after everybody leaves can still ask. So, okay, now you can pack up your stuff and go.